Every fine-tuning tutorial on this platform starts in the same place. Here's my system prompt. Here's my training config. Here's the loss curve. Nobody shows you the part that actually determines whether the model turns out any good, which is everything that happens before a single training example gets written. The data set, where it came from, why you picked it over the alternatives, what you threw away, and why. This stage is unglamorous, it doesn't screenshot well, and almost nobody covers it. This series does. I'm going to walk through the entire data pipeline behind a real project, a thinking-enabled oncology reasoning LoRA. From how do you even find usable domain data, all the way through cleaning, synthetic generation, anti-hallucination design, and final dataset assembly. Not a toy example, the actual scripts, the actual numbers, the actual trade-offs I made and why. What fine-tuning actually is and why you do it. Let's get one thing straight before we go any further. Fine-tuning is not how you teach a model new facts that change next month. If you want a model to know exactly today's stock price or next quarter's policy, that's a retrieval problem. You look it up and hand it to a model in context. Fine-tuning solves a different problem entirely. Fine-tuning, and specifically the LoRA approach I'm using here, is how you teach a model a behavior, a consistent style, a reasoning pattern it follows every single time without you having to re-explain it in the system prompt. A domain vocabulary it speaks fluently instead of approximating. When you want a model to reliably think step by step before answering, to stay inside the evidence it's given, to refuse cleanly when it doesn't know something instead of guessing confidently. That consistency is what fine-tuning buys you. A system prompt is a request. A fine-tune is a habit. LoRA, specifically low rank adaptation, means I'm not retraining the entire base model. I'm training a small set of adapter weights that sit on top of a frozen base model. That's the difference between needing a data center and needing a single workstation class GPU. It's cheaper, faster to iterate on, and for the kind of behavioral stylistic shift I'm after, it's plenty. So don't fine-tune for facts, fine-tune for behavior, reasoning style, domain fluency, and the boundaries you want the model to respect. So garbage in, garbage out. Here's the thesis of the entire series in one sentence. Your model cannot be better than the data it is trained on. That sounds obvious, it is obvious, and it is still the single most skipped step in almost every fine-tuning tutorial you've ever watched. If your source data is full of HTML entities, duplicate records, retracted studies, and broken stubs, your model doesn't magically filter that out during training. It learns it. It learns the noise right next to the signal. And in a domain like medicine, that's not a cosmetic problem. A model that's fluent in oncology language, but was trained on unfiltered, duplicated, occasionally retracted source material will sound more confident while being more wrong. Fluency without grounding is the most dangerous failure mode a domain model can have, because it's the hardest part to catch just by reading the output. So before I touch a single training example, before I write a single generation prompt, I spend real deliberate effort on 3 questions. Where did the data come from? Is it actually good? And what am I choosing to leave out on purpose? That's not a preamble to the interesting part of the project. For a domain like clinical oncology, that is the interesting part. And it's exactly where the next video starts. So where does this actually pay off? A few categories broadly. Domain reasoning assistance, legal, scientific, biomedical, where you need the model to reliably reason inside of a specific body of knowledge and specific conventions, not just answer generically. Persona and style work, where you want consistent voice and tone rather than a generic assistant register. Safety and guardrail models, trained specifically to recognize and refuse categories of harmful requests. And tool use and agentic behavior, when you want a model that reliably calls the right tool instead of guessing an answer. This series uses one of those as the flagship example, a clinical oncology reasoning assistant. I picked oncology deliberately, not because it's flashy, but because it's the hardest possible test of everything I actually care about teaching in this series. Medicine has zero tolerance for confident fabrication. It has real, freely available literature to ground the model in, PubMed abstracts, real published research, and it forces you to build an anti-hallucination machinery. Grounding checks, refusal behavior, self-correction, instead of hand-waving past it, because in this domain, hand-waving is how people get hurt. One thing I want to be completely upfront about on camera every time this comes up, this project is educational and research tooling. It is not and is never positioned as a clinical decision support system. Nothing replaces a physician. The reason oncology is a great teaching example is precisely because the stakes force rigor, not because the output is meant to sit anywhere near an actual treatment decision. Here's the series roadmap. Here's exactly what we're doing. Video 1 is the cleaning stage, finding the data sets, deciding whether they're actually good enough, and the deterministic script that turns roughly 100,000 raw records into a trustworthy clean corpus. My real numbers on what got dropped and why. Video 2 is the generation pipeline, sentence-aware chunking, and the 3 specialized question generation rounds that turn clean abstracts into structured training conversations. Video 3 is anti-hallucination design and final assembly, how grounding validation, refusal training, and self-correction sequences get built directly into the dataset, and how everything gets blended into the final SFT and DPO files. After that, separate videos cover the actual training runs, supervised fine-tuning, and then preference optimization. If you've ever wondered why your own fine-tunes came out mushy, overconfident, or just kind of generically off, I bet money the answer isn't your training config, it's upstream of it. So let's go upstream. Next video, finding, evaluating, and cleaning the actual data with the actual script on my actual screen.